They do such a wonderful job. They keep everything working, and they do any modifications to the instruments so that I don't have to build anything or test it. I can just go in and know that it's working, and I can deposit my film. If it doesn't work, it's my problem.
It's a very rewarding experience to be able to work in the microlab and really have a hands-on experience. You learn a lot of the nuances that you don't really pick up in a textbook.
You have students from so many different disciplines, and they meet and they teach each other things in here, and out pops a new direction just out of the interaction.
Thank you for your interest in the Berkeley Microfabrication Laboratory, a leading university center for the design, fabrication, and testing of microchips. This video will give you an overview of the Microlab and the wide variety of research activities it supports. But first, a bit of history. The origins of the Microlab may be found in the world's first university microelectronics and microfabrication research laboratory, built here at UC Berkeley in the early 1960s. This pioneering 1,200 square foot facility started producing working integrated circuits on 3/4 inch diameter silicon wafers in 1962.
It was pretty primitive in those days. We had no mechanical assistance for mask alignment, for instance. We were lining up 5-micron features with our bare hands. We got some working circuits, though, and we got some papers out of it, and we learned an awful lot.
The trend toward further integration through the 60s and 70s made clear the need for more sophisticated equipment and an ultra-clean work area. In 1981, the university began construction of a new 10,000 square foot Class 100 microfabrication research laboratory. The facility was completed in 1983, and the first graduate class in integrated circuits processing began in the fall of that year. Funding for the laboratory came from the state of California, industry, federal agencies, and the regents of the University of California. The total cost in 1980 was $4.57 million. Professor William Oldham was the driving force behind the creation of the new lab.
The great thing about the Microlab is the way it evolves. Having such a wide variety of technologies under one roof with brilliant students and a terrific staff fosters innovation, adventures which repeatedly take it in new directions.
Professor Ping Ko became the first faculty director in 1985. Professor Costas Spanos succeeded him in 1993 and was followed by Professor Sujay King in 2000.
I expect that the needs of the faculty doing research in the Microlab will continue to evolve, and so we will have to adapt continually to meet those needs.
The UC Berkeley Microlab contains everything needed to design, fabricate, and assemble integrated circuits, sensors, and optoelectronic and superconducting devices. Among the 130 operative systems, there are computer workstations with graphics capability, mask-making equipment, photolithography equipment, thin film systems, high-temperature and LPCVD furnaces, plasma etching systems, and a variety of inline test equipment.
My favorite machine. They're all so nice.
In 2001, the Microlab undertook an extensive 6-inch upgrade to better meet industry requirements. Several TiStar furnaces can now deposit nitride, polysilicon, and low-temperature oxide on both 4-inch and 6-inch substrates. In addition, it is now possible to oxidize, anneal, and deposit silicon germanium on both 4- and 6-inch wafers. The 6-inch upgrade has made possible the acquisition of other state-of-the-art equipment, such as the ASML 5590 DUV stepper. The stepper uses a Cymer laser with a wavelength of 248 nanometers to expose the resist. The tool is designed to address a 0.35 micron technology node, but it can easily resolve 0.25 micron lines and spaces. And the Advanced Lithography Group at Berkeley has plans to resolve 0.1 micron features by applying techniques such as phase shift mask and off-axis illumination. All aspects of Microlab operations are overseen by specially designed computer software. The software controls and monitors equipment usage and maintenance. It performs administrative functions and provides direct data retrieval for statistical process control. In addition, the system keeps track of qualified users. Those wishing to do research in the Microlab must attend a full-day orientation course given by lab staff and experienced lab members. Before being allowed access to the lab, new members are tested in their knowledge of safety and cleanroom procedures. Lab members learn to operate machines by reading the online equipment manual and by arranging training sessions with experienced users. Members are designated qualified on a particular machine after demonstrating proficiency on both a written and oral examination.
The great thing about working in the Microlab has been that there's so many users available to give you information on setting up your process that things can get rolling very fast.
The Microlab is accessible with a card key 24 hours a day, 7 days a week. The only restriction is that no one may work alone.
Good morning, you've reached the Microlab.
Over 30 staff members help to maintain the Microlab as a safe, efficient facility. Catalin Voros, laboratory manager since 1986, has assembled an exemplary support staff. Bob Hamilton, facilities manager, oversees a highly skilled maintenance staff responsible for all lab equipment and satellite facilities. With the help of her staff, administrative manager Rosemary Spivey keeps track of more than 300 lab members and their accounts. In addition, she manages recharge accounting as well as purchasing and inventory. Process engineering manager Sia Parsa heads the process support group. Process staff develop, maintain, and monitor standard processes in each piece of equipment. They assist students with process design and troubleshoot difficult problems. Process staff maintain a 1-micron CMOS baseline. The cost of operating the Microlab was $2.5 million in fiscal year 2000-2001. The Microlab is a recharge operation, which means that operating costs are met by lab user charges. Microelectronics research in the Microlab falls into 3 main categories: silicon, compound semiconductors, and superconductors. Of these, silicon represents the largest research endeavor, spanning the areas of integrated circuits and advanced devices, technology innovation, and integrated sensors and actuators, or MEMS. Although the majority of work is in microelectronics, research is by no means confined to that field. Microfabrication techniques and equipment lend themselves to a wide variety of research activities. About 50% of the students using the Microlab are affiliated with the Electrical Engineering and Computer Sciences Department. Others come from the departments of Physics, Material Science and Engineering, Chemistry and Chemical Engineering, Mechanical Engineering, and Bioengineering.
It's very interdisciplinary. You get to meet all kinds of people doing different things, and that helps you be more creative with your own work.
The Microlab serves a wide variety of research interests. Students in the device research group develop techniques for processing very small, deep submicron metal oxide semiconductor devices. Often, new physical phenomena are discovered using novel test structures. In the Microlab, students can design and process these ultra-small devices themselves. The cooperation of the device group and the Microlab has produced many exciting research results, such as FinFET, a device that may make it possible to squeeze 400 times as many transistors onto a silicon chip. Students also built the popular BSIM and BERT simulation tools based partly on devices fabricated in the Microlab.
For almost 3 decades now, the semiconductor industry has relied on a single set of materials, namely polycrystalline silicon and silicon dioxide in the front end of the transistor fabrication process. And it is very well established now that in about 3 to 4 years' time, industry will have to start using new materials in the front end of the CMOS process to ensure continued scaling. My research is in the general area of semiconductor processing, and in particular I'm trying to investigate new materials and processes for use in future CMOS devices. We're trying to look at high permittivity dielectric materials and metal gate electrodes in particular.
As transistors are made smaller, all the dimensions need to become smaller, and as a result, the parasitic leakage currents increase. In order to allow scaling to continue while reducing the leakage currents, we're looking at a different material, silicon nitride, to be used as the gate dielectric in MOS transistors. As manager of the Device Characterization Lab, I'm always looking for ways to make the lab a better place. This lab is an integral part of the research of the device group. The Microlab has given us excellent support in maintaining our utilities such as nitrogen and vacuum, and recently they managed a major renovation which included the installation of air conditioning and HEPA filters.
The push for more transistors on each chip and for smaller line widths has led lithographers to use a variety of techniques, such as high numerical aperture optics, modified illumination, in-lens filtering and phase shift masks, chemically amplified resists, and special substrate preparation. The Advanced Lithography Group employs these techniques in such projects as photoresist resolution enhancement and deep UV photolithography. These research projects have led to the development of such innovative tools as the Sample Process Simulator and TCAD frameworks for IC topography modeling.
What I'm looking at actually is the materials, in this case photoresist, and looking at the molecular structure of the materials themselves to see if this has some sort of defining point in the lineage roughness. Lineage roughness is sort of a noise of roughness along the pattern you're trying to create. Something that we've recently come upon in the past 6 months or so is using atomic force microscopy. Usually that's used for top surface roughness, and we're trying to use it for roughness along an edge, which is kind of difficult because it's actually a needle that comes down and tries to usually rub the surface, in this case reach under, rub along the sidewall.
In today's competitive semiconductor industry, companies are driven to improve the manufacturing process to maintain high yield in production. The BCAM Group, the Berkeley Computer Aided Manufacturing Group, conducts research in the areas of semiconductor equipment, fault detection, diagnosis, and control. Students in the BCAM Group conduct experiments on equipment in the Microlab to develop monitoring software. This software is then tied to the BCAM manufacturing framework, which tracks much of the CMOS equipment in the lab.
My research focuses on the placement of sensors and also electronics, a power source, and a communication system right onto the surface of a wafer so that you can take that wafer and put it into a processing chamber. While it's inside, it will sense what's going on and transmit that information out to you so that you can then either close a control loop around the equipment and tune it in real time, or you can diagnose equipment problems that way. Since you're placing electronics and batteries onto the wafer, they have an intrinsic limit of about 150 or 200 degrees Celsius, which limits us from using these things in, for example, RTP or CVD chambers where the temperature is much more elevated than that. So one of the things that we'd like to be able to do is build a very good thermal insulation around the electronics and the battery to keep them at low temperature while the wafer is at high temperature so that it can be used in these processes.
The performance of optoelectronic devices continues to improve by orders of magnitude. These devices have promising applications in optical communication, switching and interconnects, printing, display, and storage, and biotechnology. Here at Berkeley, we're actively engaged in researching a variety of advanced optoelectronic devices with wavelengths ranging from the visible to 1.6 microns. Areas of study include fundamental device physics, modeling and novel device design, advanced processing, and optical characterizations. Projects in semiconductor lasers have had record-breaking results. These projects include wafer-scale fabrication of two-dimensional vertical cavity surface-emitting lasers, known as VCSELs, and arrays with ultra-high bandwidth, widely tunable lasers with integrated micromechanically tuned mirrors, beam-steerable angled facet dry-etched lasers, VCSEL with integrated detectors, and high-frequency modulation and mode-locked VCSELs. These projects continue to push the frontiers of device physics.
Vertical cavity surface-emitting laser is my research topic, and mainly I'm interested in trying to bring up the speed of the device. Typically, the oxide confinement VCSEL is the way to go because it has better stability in terms of the electronic property and also optical property. But then you run into the problem of having a parasitic capacitance that actually limit the speed response of your device. So we try to minimize the parasitic, is try to add in another proton implantation process, trying to reduce the parasitics, and then we can modulate the laser at even higher speed.
From its inception, the Microlab has been a place of technical collaboration with the industrial community. In 1997, under the leadership of Professor Spanos, one aspect of this relationship was formalized as the BMLA. By giving industry researchers access to a clean room, many startups have been able to establish themselves in a capital-intensive industry. Companies pay a membership fee per year per person and standard laboratory fees with overhead. Applications are reviewed and approved pending an assessment of resource availability in the lab. BMLA member companies are comprised mostly of small startups and alumni. With the access it provides, the Microlab serves as an incubator for California high-tech industry.
I work for a company called Covalent Materials, where we're trying to commercialize nanotechnology. We make the world's smallest diodes and transistors to be the heart of tomorrow's computers. The future of electronics is moving gradually away from conventional silicon and silicon dioxide materials. One of the advantages of the Microlab is that without too much investment, we can play with substituting one material at a time in conventional technologies. It doubles or triples the experimental facility available to my company at a fraction of the cost.
Silicon-based micromachines are the subject of continuing research at the Berkeley Sensor and Actuator Center, or BSAC. Sensors are devices that passively transform physical inputs, like temperature or inertia, into electrical responses. Actuators are capable of mechanical motion using electrical or magnetic inputs to generate work. Typical examples are micropositioners, micromotors, miniature fluid valves, microchisels, optical choppers, grippers, and miniature fluid flow systems. Both sensors and actuators can be fabricated using conventional planar thin film processing available in the Microlab. There is a rich vein of potential applications for micro-electromechanical systems, or MEMS. One example is BSAC's work on developing a chemical plant on a chip. BSAC students can also experiment with new materials, such as polymers and piezoelectrics. Combining flexibility with well-maintained baseline technologies, students in the BSAC group have excellent opportunities for research as well as technological innovation.
My group is working on MEMS for adaptive optics, and we're trying to build a deformable mirror that is used to correct aberrations in the atmosphere. And what we're trying to do is figure out how high of a quality mirror we can make to do that with, how fast it can move, how far it can move, and so forth. It's pretty exciting where this will go. So far with the MEMS, the thing that it really brings us is we can make really inexpensive deformable mirrors with thousands of actuators. So at this point we've developed sort of small scale 7 mirrors that move around. The next step is to integrate these with electronics and then to start making thousands of them, making a big array.
I work on making neural probes, and these are silicon-based probes that are used to collect data in the brain, the visual cortex. One of my problems is in reducing the cross-sectional area and yet keeping the probes stiff enough so that they can be poked in, taking the data without breaking. I think the Microlab is really great for students who are trying to develop new processes, for example, polymeric needles, because there are traditional fabrication tools such as plasma etchers and Thailand furnaces, and there's also the old lab where they have sinks and other places where we can try new chemistries, surface modifications. So the Microlab has really been great for bioengineers, I think.
From the days of the first pioneering experimental facilities in the 1960s to the present modern laboratory, Microlab users have pursued a wide variety of subjects at the cutting edge of technology. The pursuit of new ideas, education, and discovery is what the Berkeley Microlab is all about.
Is to let you carry out an idea. You get an idea and you carry it out. It's a place where you can actually pull off some of the crazy things you want to do.